Welcome everyone. Today we are going to do a short introduction to electronics. If you are new here, this course is a part of a European Parliament project that has sponsored us here at FabLab Nordvest to teach both teachers and students around Europe about technology and help them become better at understanding this so we can all work forward with it together. This is going to be the first of a series of 4 lectures combined with small videos of examples. This first one, exciting, This first one is about components and basic electricity. We're going to work from this into Arduino, digital electronics, and finally into 3D printing. These things are all connected, and we're going to just briefly cover these topics so everyone else who have joined us here can go out and explore this topic on their own and feel a little more comfortable doing so. Hopefully we'll see a couple of talents in a couple of years doing what I'm doing here today. Just shortly, I'm Anton. I'm a part of FabLab Nordvest. I'm almost an engineer, finally. It's been almost 5.5 years of studying. I have worked a lot with designing mechatronic prototypes. Mechatronics is the mix between electronics and mechanical products, so basically just small robots. I have a 3D printer in my room and I do enjoy working with Arduino a lot, so I am happy to be here teaching everyone a little bit about what I think is really fun. So let's get into it. First of all, just a bit of theory. For most of you, this might be either redundant or you don't care much about these basics, but I do think it's kind of nice when you do understand what's really going on, even on a molecular level, which is what we're talking about here. This is the atom, and I'm covering it because I like to talk about things going in depth a little bit, even though this is a brief presentation. Why we talk about the atom is because we're talking about electricity. And electricity is the energy that is released when charged particles are displaced or moved. And in this regards, we're mostly talking about the electrons, which is a part of the atom. It is these small particles that are moving around, creating charges, and that's what we utilize to get a LED to charge and light up, or a resistor to resist this current. So, in short, there's been a lot of talk about what electricity actually is and what type of energy we're harvesting. People have this idea of a chain of electrons moving back and forth in a wire. This is not necessarily a bad understanding, but not the most accurate. It's actually more like this, which I think you need to change the battery on this after we're done. When an electron starts to move from one direction to the other or back and forth, it will create a magnetic field where in this magnetic field the energy is transferred. And when this magnetic field is created, all the other electrons will start moving. Additionally, people have an idea of electrons just moving from one side of a wire to the other instantly. That's not how it works in reality. The movement of an electron is chaotic. Even though it's motivated to maybe move from one direction to the other, it's not going to do so in a straight line. So in fact, it only moves a couple of millimeters every second in a direction. However, it does move extremely fast, just not in a straight line. And as I said, there is going to be something that needs this, or that motivates this movement. Mostly we're looking at either magnets or batteries. Magnets are, you can say, small pieces of iron where certain elements of them are aligned to allow for a magnetic field to be created, and batteries have a chemical displacement of electrons that creates a voltage that motivates the electrons to move. And these two types of electricity, you can say either forced by magnets or forced by chemical energy, are very common, and we see them a lot. And this motivation, we measure that using something we call voltage. And then there is the not only voltage, there's also the current of flowing of electrons and the resistance to this flow. And the best analogy, or at least the most common analogy I've seen, is the use of water to really understand this, where we can consider ohm to be the tap, the resistance towards the movement of the water through this pipe. Or we can consider ampere, the current, to be the actual water that flows through the system. And voltage can be the pressure that pushes the water to move forward. These relate to one another in what we call Ohm's law. Quite often you will see this triangle where you have the voltage on the top, you have symbolized by the V, the resistance symbolized by the R, current symbolized by the I. The I is related to the current because of the intensity of the electricity, so it's this I from intensity that is represented here. And when you want to know what one of them is and you have the two other ones, what you do is you place your hand on one of them. Let's say you put your hand on the V, and then you can see you just have to multiply the resistance to the current. Or if you want the resistance, you divide the voltage with the current. That is what we call Ohm's law, and you'll see this many places. As we saw in this former triangle, you can see the resistance at the bottom. Or what if the resistance is, you can say, extremely high and the voltage is super low? Then we will see that the current is going to move towards zero. This is what some materials, you can say, do to electricity. That is what we call insulators. That are materials that don't allow electrons to move at all because the resistance is super high. And then we have the conductors on the other hand, where electricity can move almost freely. Most of you might have seen a wire that's insulated by a sort of rubber material, and on the inside you have a copper, which is a great conductor. Other metals like gold could also be used, but that is a little expensive. Generally, we talk about two types of electricity. One type is the alternating current electricity, AC, and the other one is direct current. Direct current is just with the batteries, where we have the electrons moving in one direction, being motivated all the time to move in the same pattern. Where the alternating current is like a rotating magnet, the electrons moving back and forth. What is really interesting is that the energy in fact moves in the same direction, even though the electrons move back and forth. This is due to some very complex math, and we're not going to get into that here, but just understand that these magnetic fields work transferring this energy even though we might push the electrons back and forth or push them in one direction. That being said, there are certain restrictions to each type of electricity. We use the direct current a lot when we work with computers, for example, because all the components that are used in the digital electronics universe need this type of electricity to work. And then we have the alternating current, which is mostly used to transport electricity over extremely large distances into, for example, households from a not a power supply, a power plant, which is what it's really great for, transferring power over these large distances. And that's why you will have them in your plugs at home. Going into the components, I figured we maybe just should change the battery on this real quick. I have which... Oh, no. Flying batteries. Whoop. That was wild. Just 2 seconds. There we go. Super. Good, then we're ready for the second half. Components. So again, we're going to use this water analogy. It's really useful. None of them are perfect, but it will allow us to understand what these different components do in relation to this electronic circuit. First, let's talk resistors. As I mentioned earlier, you can consider them a tab if you can kind of change the resistance, but most often they'll be looking just like this, for example. This is a simple resistor with a value similar to something like this, just a little bit larger. As you can see, it has this one says 12K, which means 12,000 ohm. We use these to protect components which cannot handle a lot of current. When we do this, however, we change you can say the current of electricity into heat. So do be aware that if you have some very high resistors on flows of electricity with a lot of current, you might experience that they become rather hot when you work with them. And then there are, as I mentioned, resistors where you can change the resistance. That is what we call a potentiometer. And these are very often used in small Arduino projects where you want to maybe dim a light or choose between different functions in the Arduino circuit. There is. Oh yeah, there is. Here. This one we haven't had the chance to plug the handle in, but you can see here there's an interface where we could add this, and then you could turn it back and forth, changing the resistance for your personal needs. And as you might have seen, some of these have, or all of them have color codes reflecting some value of resistance. You can use these to determine how much value it has. I more often than not just use a voltmeter to check them, just put it on the resistance symbol and measure it. I find that to be more accurate and easy, and then I just try to keep them in semi-order. With projects like this, I try to keep them together with the other 12Ks, but when you mess it up, and you eventually will, it is nice to just kind of check it. Then we have the capacitors, which is something like this. Capacitors you can consider kind of a container of water. They fill up a little slowly, they have a certain capacity to hold, and then the electricity will flow out as well. This one is polar, meaning it has a negative and a positive side. Some of them work both ways. This one works one direction, and you can see the line here with the white would normally indicate the negative side. These are very useful to create either oscillating circuits. That could be an astable multivibrator, or we use them to maybe protect parts that cannot have a large change in flow. So sometimes we use these to make a more steady flow of electrons in the circuit. And as I mentioned, there are two different ones, one being polar, one working in both directions. The ones working in both directions quite often are really small ceramic capacitors that look like the small one you have here on the screen. Then we have batteries. In comparison with the capacitor, which we kind of had like a small container of water, you can consider a battery more like a water tower. It has a lot of energy stored to move electrons. And like water towers are displaced from the ground to be able to push the water into the taps or in the houses. Batteries have a certain voltage that pushes these electrons from the negative to the positive side of the circuit. Then we have elements like push buttons. I unfortunately don't have one here right now. It's a really simple component. As the water explains, it's just kind of you can say a button that allows for water to flow through when we push it, and when we don't push it, nothing happens. This is a very simple kind of sensor that would register your touch, and we use them all the time when we prototype. If we want to know whether they're good or bad, or if they are used in the right way, we can just put our voltmeter on the resistance symbol and then put it on both legs and then push the button, and hopefully we'll see it go to 0. I've used this a lot, this type of logic, when working with old electronics. I have an old motorbike that I probably spend more time repairing than I do driving, and a big part of it is fixing all these old terrible electronics. And doing this, you can really see whether or not you have a good connection or not. Then we have transistors, these small types of things. They are super useful and they are used a lot. They are similar to the push button in the way that they either allow for a flow or don't allow for a flow. But where the push button is a mechanical product where we physically push it, the transistor is controlled by electricity. So you can consider it a light cone from a traffic crossing. There are many types of transistors and they're actually rather complicated in terms of how they're created. But most commonly we use one or two different transistors when we're prototyping, either a NPN transistor or a PNP transistor. The PNP transistor will let the water flow until it's activated and then it will stop. And the NPN transistor will not allow for flow until it's activated. And then when we activate it, the flow will go through. So it's kind of a do something until we tell you not to, or do nothing until we tell you to. Then we have diodes. Diodes rectify the current, or basically the current can only move in one direction through them, and then we can use them to rectify it. The most, I would say, used, or not necessarily the most used, but the diode that most of you probably know or have worked with is the light emitting diode, which is the LED, like this. The LED has a cathode and an anode. We can see that it has a slightly flatter side here, which symbolizes the negative side. And also we might see a difference in the distance on the legs, where the long one is positive. However, if you work with prototyping, you know that quite often you actually start cutting these according to what circuit you're doing, and then that won't work anymore. So it's good to know that there's a flat side being the negative. So these are the quick components that we've covered so far, and their symbols. All electronics, when we kind of use them in a context of this, will be shown in symbols. Sometimes online now you will find figures of circuits where they've used small models of the actual component instead. That is starting to become a new standard with prototyping. But working professionally with this, you will need to learn these symbols if you want to keep expanding your horizon. And how do we mount them? There is kind of a either or situation. We do either soldering, which is where you melt soldering tin with a soldering iron and you mount it onto the plate. You have the soldering tin here and the soldering iron, and you can mount them onto a plate like this, which is called a printed circuit board, where you can see all these small copper rings. That is where we would like to mount our components. And on this side you can see different symbols for the components for this specific circuit. So that is a very common element to use. Then we can use something like this, where we avoid the soldering. This is called a breadboard. We're going to talk a little bit about them later as well. Basically here we clamp the components because the entrance has a small clamp in it, where we can connect the components to copper wires or copper thread that lies beneath the plastic in a pattern. So this is really smart when we're prototyping, but for professional circuits it's much more common to use these, as the connection in those, like in these breadboards, can kind of go bad. So we prefer this when we're moving into a more finalized product. And some of you might be sitting here right now thinking that this is really, like, how do you even get started? And I just want to say that this model I have here is a power supply with a voltage regulator in it. And I taught some kids how to build this just using their knowledge of simple symbols and simple soldering and just slowly working their way through it. And I know that you can too, if you choose to do so. There's a lot of these online, and it's really just about just taking your time and translating what you see in front of you on these small symbols into components, and then just solder them very slowly onto the board. The far majority of the components in even quite advanced circuits are the components that we've covered here today. There might be some components where these are built into it. That could be something like the processor on this board. But more often than not, it is just these basic components that we use when we create these simple small circuits. Just a few tips when you do solder. I unfortunately don't have anything here right now, but if you are challenged with soldering to certain surfaces, that might be because there is a coating on it that won't allow you to actually solder to it. And we can help this in two ways. We can either heat the surface, hoping that we can burn this surface away that doesn't allow for soldering, or this coating, or we can use what is called flux, which is kind of this soapy material that you would find in most electronic stores, and it would also be in most soldering kits if you buy a soldering iron together with some clippers and such. And then just a couple of the other tools that are really, really useful. Pliers like these are great. This type of plier allows for different sizes of wire to be de-insulated. This is a staple when you work with electronics, I'd say. But if you are more experienced, you can also just use simple pliers like these. And if you're really crazy, you might even just use your teeth. I've seen my dad do that a million times, but it's not something I'm going to recommend going forward. Also just simple sponges like these, add water to them and use them to remove the extra soldering tin from your soldering iron as you're soldering. As we continuously heat soldering tin, we will have a reduction in the flux that is in the soldering tin. So you can say the soldering tin kind of goes bad after some time when it's been on your soldering iron for a while. That's why we will circulate it using these to remove them slowly, and then just keep using fresh tin. Hello everyone, this is just going to be a short example video of how to work in Tinkercad with electronics. What you see in front of you here is just a simple LED setup. So I just want to show some of the functions. This is the return button. It's called Tinkercad as is in here. When we want to turn on things, we press here for start simulation. If we're doing Arduino, as we're going to be doing later, we have the code function here. And then we have a lot of different components here in the basic components, all components, Arduino related components, etc. So what I've made here is just a simple push button, LED resistor setup. And then if I press start simulation, press the button with my left button, you can see the LED lights up. So how does it work building just a simple little small circuit like this? I am going to show you. First we're going to stop the simulation. So let's first of all grab a battery here. What we can do is here we have a mirror button and a turn button. We can either rotate it, or we can mirror, or we can jump it like this, mirror it around. A lot of different functions here, but let's just do it like this for now. Grabbing an LED, as I have mentioned, there is the I'm just gonna flip this back actually, so we have the plus on the right side. No, then it is right. Good. The flat side here of the LED is the anode, the minus part. So let's keep it like this. Let me just check here. When we press resistors, we can see the value here and the name that we're going to give it. For this, it's a 407 ohm. You can use different like mini, micro, kilo, mega, giga, but let's just have an ohm for now. So grabbing a resistor, we can either do like this, of course, add it to 370, not kilo ohm, but just ohm, or we can press this one, Control C, Control V, and we have another one. So just to show some of the functionality. Wiring we have up here. So we press here. We say we want to do just a normal one. Positive, let's keep it red for now. So we have the color one right here. Let's go like this. And then we're going to do from this one to this one. Then we add a push button here. Let's, on the other side of the LED for now, just keep it black because we're kind of going the negative way now. And going back. So let's see if it works. Boom, it does. So that was just a very short tutorial here on how to build just this simple circuit. There are obviously a lot more, but there's no reason to go into that for you, but I do recommend that you do this for yourself. Get onto Tinkercad and try just working with these small setups. That's it for the basic electronics part. I'm going to continue on working with videos like these for both the Arduino IDE and how to work with Arduino in this setup and how it looks when you connect a real Arduino to a computer. Have a great time going forward. Endorsement out.